we used just a dead simple argument that you cannot get around, which is watch how long it takes for the brightness of an object, it's random, unpredictable brightness changes, to change dramatically. How much time does it take? And that gives you an upper limit to how large the region is where all of this luminosity is coming from, the distance that light can travel in that amount of time. And this is an amazingly powerful constraint because it turns out that some of these objects are so strongly, rapidly. Two more examples to show you. The thing became ridiculously bright. This is how bright it was in the gamma rays, much, much brighter than the Milky Way galaxy over just a matter of hours. And then it faded back. Another very famous example, there's a light curve taken with an X-ray telescope, Chandra, which had high magnification, so it could look at all of the complicated X-ray emission coming from our galactic center. And here's how many X-ray counts were measured when looking just at the exact center, the so-called Sagittarius A star. X-ray emission from this object got ridiculously brighter and then almost went away over just a course of a few hours. This one you all should know. So I've just got two equations here from this chapter 3 of Brad Peterson's book on AGN, the so-called Eddington Limit, limiting luminosity above which the outer layers, assuming they're made of hydrogen or anything, basically they're made of atoms, the outer layers of the object producing the luminosity would be blown off and explode, and the object would go away by what force? Radiation force on the individual atoms would become, at the Eddington limit, equal to or greater than the force of gravity holding the entire object together. This is a pretty conservative limit. There's really no way around it because every object is made of atoms, and the atoms are made of, for example, electrons, and electrons, when you shine photons on them, have a very small cross-section where they might absorb some momentum and therefore feel a force from those photons. If there's a ton of photons per second pouring out there, then those electrons might feel a substantial force and a substantial acceleration outwards. And the Eddington limit says, at what point does the outward force of this radiation pressure exceed the gravitational force, gmm over r squared, that's holding an atom in there? Now you notice that the gmm over r squared is the force on a proton, because that's where most of the gravity acts on something that's made of hydrogen, for example, whereas the force of radiation, that's the Thomson cross-section, the cross-section of photons pushing on electrons, 10 to the 31 watts for an object having a gravity of 1 solar mass. And so you can scale this to any mass you want. Force, explosive force outward of radiation pressure is a 1 over r squared force, but gravity is also a 1 over r squared force. So this argument does not depend on where the material is, doesn't depend on how big the object is. You can't get away from the Eddington limit. So could we apply this to the sun? It would have to be 10 to the 38 ergs per second, a bit more than that of luminosity. But the sun, of course, is not that. It is 4 times 10 to the 26 watts. So the sun is in no danger of blowing itself up because it's nowhere near 10 to the 31. Supergiant star can be 10,000 or 100,000 times more luminous than the sun without really being that much more massive. The most massive stars, at least at some phases of their lifetime, are in fact somewhat getting to the Eddington limit as they do blow off layers of their outer shells, and they eventually kind of evaporate. What if I put in a quasar luminosity, and I've already shown you some where the luminosity is much more than the Milky Way galaxy, 10 to the 38 watts. What does this Eddington formula immediately tell you about the source of the energy in that quasar? It has to be very high mass. For many of the objects we're talking about here, it has to be at least 10 to the 7, maybe 10 to the 8, and in some cases 10 to the 9. That's a billion times the mass of the sun. So we're talking about this much mass in a very small region that's probably smaller than the solar system. First thing is, it was very small. Second thing we know, it's very, very massive. You know, all the luminosity in the universe pretty much comes from some mass getting converted into energy. The only question is, what is the efficiency? Tell me what this efficiency factor eta is for the most efficient thermonuclear fusion reaction that we have, which powers main sequence stars, the conversion of 4 hydrogens into a helium, resulting in a little bit less mass at the end of the reaction. How much mass is converted into energy? 0.7%. So that is really not very efficient. And the highest gravitational acceleration you get would be very close to this event horizon of a black hole, because that's the place where you can potentially have matter falling in that gets accelerated just about up to the speed of light. But in the process of doing that, it's going to require an enormous amount of kinetic energy. And so the trick would be if some of that incredible kinetic energy, which is basically just gravity power, could be converted into radiation. Since this is a very great paradox of astronomy, how could the darkest object in the universe, a black hole that doesn't let any light or anything escape from inside its event horizon, how could that be associated with the most luminous objects in the universe? And of course, the trick here is if the luminosity is produced outside of the event horizon, but not too far outside, where the gravitational accelerations are the strongest. He put in a very much higher efficiency, right? 10% efficiency of matter and getting converted into pure energy. Suppose that we were doing this just by fusion. You just have to have so much fuel in there. It's a little hard to imagine. 30 times the mass of the sun per year just to feed a typical quasar. This is not an airtight argument, but it is strongly suggestive that we need something more efficient than old hydrogen fusion. Close-up picture of M87, a giant elliptical galaxy. Here's a not very bright point of light in the middle that's not stars, low-power quasar. Pretty straight jet that clearly is coming out of the center of this galaxy where the energy generation that is coming, where the AGN is. So AGNs blast out in some cases, not all cases. We don't know exactly why they don't all do it, but they have a tendency to blast out jets of energy. These are very, very high energy electrons, enormous energies that allows them to produce synchrotron emission, high energy electrons cycling around in a magnetic field at a very high speed in a very highly collimated direction. In fact, there's usually 2 directions. It looks bipolar. This is a cosmic zoom of the same object. The highest magnification is similar to what I was showing you before. Of course, with radio telescopes to get that kind of magnification that was in, this is a Hubble Space Telescope picture, optical picture, which this jet is emitting synchrotron emission, but it's also emitting a lot of radio waves. Looks very straight here. But in fact, on a larger scale, you see that it's going out in 2 different directions here. And these are huge, hundreds of thousands of light years across. It has been doing this for a long time. Cygnus A, the brightest radio source in Cygnus, which is the center of a galaxy. Galaxy's right here in the center. See my little cursor there? Blasting out these 2 bipolar jets into intergalactic space. It's an enormous amount of power that over millions of years has been dumped into these lobes. These are double lobe radio sources. Here's another example here, Fornax A. The actual galaxy is just right here at the center. The AGN is right there in the center. It's tiny, but it's managing to deliver energy, what? In a very stable bipolar direction for a long time. So what do we just learn? Any AGN have a gyroscopic axis, which is quite stable. They know a certain direction, and they put out energy to some extent in that direction for a long, stable time. And so you have to think of some object that's very massive, has a huge amount of gravity, but also has a gyroscopic stability. Strongly suggests some kind of rotation. These high-energy particles are accelerated along the spin axis of an accreting black hole, because that's the easiest direction to generate enormous electric and magnetic fields and to accelerate particles to high speed. Probably the spin or the axis of these giant black holes is determined by the angular momentum of the material that they're consuming, to the gas which accretes onto a black hole. As it falls closer and closer, it's going to start having a lot of rotation. It probably settles down into some kind of a disk. In fact, I'll show you direct evidence of that. These jets are probably being blasted out of the poles. If a black hole has been feeding for some time from material that generally has one direction of angular momentum, then it's going to start spinning in that same direction. The spin of the black hole and the spin of the material right now is generally not the same as the spin axis of the galaxy. This does sort of look like a disk in the galaxy, and it does kind of look like the radio jets shown in orange are blasting out of the poles of the disk. That's strongly indicative. Give you circumstantial evidence and theories and whatever that we need enormous mass and enormous gravity in a small space that is converting fuel or accreting mass into energy at a lot of wavelengths by converting gravity power into accretion power. Most popular leading theory is that the matter spirals down into the black hole. You need to have some kind of friction as the material spirals faster and faster into the black hole. If it was very empty, material was just free falling into the event horizon without interacting with anything, it wouldn't necessarily produce much to see. Friction will make it heat. This actually does happen in accretion disks, and we've seen them in many places, so we understand how this works. The inner regions are going faster than the outer regions, trying to pass by the slow-moving regions. It's like a freeway where things are not going the same speeds. Now, thank goodness there's not much friction on a freeway, but if there is friction in the accretion disk, then energy is going to get transferred outward, and angular momentum is going to get transferred outward. The result is the matter loses its angular momentum, its orbit gradually decays, and it gets hot. How hot? Tens of thousands of degrees, 50,000 degrees, 100,000 degrees. In some cases, in the inner parts where things are going really fast, could get up to hundreds of thousands. It causes it to radiate, actually black body radiation. Now, the reason this theory was strongly considered is because it was first applied to stellar black hole systems, which definitely have an accretion disk, like Cygnus X1. Where does the accretion disk come from? Where does the fuel come from? It's lucky. It's in a close binary system, a tiny little thing, but it's in a close orbit with a very massive giant star, which is losing its outer layers, and these outer layers are spiraling down onto the event horizon of Cygnus X1. So people already knew about the accretion disk theory for X-ray sources, but it was a pretty big leap of faith. Gas in the centers of galaxies is feeding giant black holes because you need to have black holes, giant black holes, kind of waiting there to get fueled in the centers of most galaxies. However, with a lot of work, the evidence kept piling up that that is exactly the truth. You look at the orbital motions of material just outside of the center of the galaxy, but in the central region of the galaxy. This is a close-up Space Telescope picture of the same system that I showed you a few slides ago. Remember the giant elliptical galaxy, Messier 87? M87 played a very big role in this because it's one of the nearest big black holes that you can study up close, with one other exception, our own Milky Way. This is the other nearest one. This is a spectrum along this slit. The north side, here's the south side of it. And what do you see? This is the velocity of hydrogen gas. Just outside the nucleus, it is hugely blue shift, 1,000 kilometers a second. Just a little bit to the south of the center of the galaxy, it's moving around at a huge redshift, like 1,000 kilometers a second the other way. This fall off here, V goes like the square root of 1 over R. V equals square root of G M over R. This just looks like a solar system or a Keplerian rotation curve going around what? A single mass. In Kepler's case, it's the mass of the sun. Here, M is the mass of the central object, which turns out to be enormous. We now know it's several billion times the sun's mass in a very small volume here. But seeing the orbital motions of stuff around it was really the proof. This is the smoking gun. So there is the central X-ray source, is the dynamical center of the Milky Way galaxy, Sagittarius A star, right there. And aside from a weird X-ray source and a very weird radio source, there's not much else there. With the magic of adaptive optics, see all of these individual stars orbiting around. What are they going to orbit around? They have to orbit around the center of mass. This is very clearly the center of mass. They're going so fast, particularly the ones that are at very small r. Keplerian velocities here of all of these stars, with m being 3.5 times 10 to the 6 solar masses. Look at what all these stars did from 1995. We'll follow them for, I don't know, about 24 years here. The little dotted lines, ooh, some of them had some really close approaches there. Some of these are highly eccentric orbits. Look at that yellow one in particular, SO2. It's coming around now and has just passed its second closest encounter. Because it's going around very close to a point mass, it's now claimed that this ellipse here is actually precessing exactly the way general relativity predicts. 3 different pictures here of the center of a not interesting galaxy. This one is a WIMP. It has a very weak AGN in the center. It does have one advantage. It's a fairly nearby spiral. There you can see it. It's a fairly edge-on spiral, and there's the center of the spiral. Radio jet coming out of it. Aha, well, you guys are thinking, okay, radio jet. So the theory suggests that that might mean that there's an accreting black hole, and this is the north and south pole. Here is a super high magnification image. So this is the radio jet. That's the exact center of mass of the galaxy. There's a black hole there. The radio jet's coming out of the north and south pole, but look at what else they found, and they weren't even looking for this. This is just by accident. These little dots here are water masers, a scale of like hundredths of a parsec. How could they possibly do that? Because water masers can be very bright and very compact. If you observe them, how could you observe them at this resolution? You have to use the entire platform of the Earth for very long baseline interferometry. All of the water masers on the east side of the galaxy are redshifted, so that with high velocity, and all of these blue ones moving towards us at very high velocity. See that line there? It's exactly V equals square root of GM of R. And of course, that's the same mass over there. It's about 1,000 kilometers redshift and 1,000 kilometers a second blue shift, because all of the mass is concentrated at the center, and we know exactly what the mass is. VLBI is so beautiful, it actually has measured these water megamasers accelerating around in their orbits, just like the UCLA GES group does of stars going around the Milky Way. But this is in a distant, fairly far away galaxy. So we actually know exactly how far away this galaxy is, because a linear velocity translates into an angular velocity only if you know the right distance. That all of the other galaxies where the evidence is much less good, probably the same thing. 3 famous objects that I showed you so far, M87, Sagittarius A star, and NGC 4258, don't really show all of these universal defining characteristics of an AGN, but most of them do. There is an average spectrum of an average quasar there, from optical wavelengths over here on the right side all the way down to ultraviolet wavelengths over here. Now, these spectra were taken with optical telescopes. I wonder how they managed to measure all of these ultraviolet emission lines here. High redshifts, you got it, where the wavelengths have been stretched out, lengthened by factors of 2 or 3 or 4 times their original rest wavelength. The first thing I want you to notice is highly ionized gas, such as we have not generally encountered around normal galaxies in the Milky Way. For example, carbon-4, it's lost 3 electrons. There's another one. Silicon lost 3 electrons. And nitrogen, by the way, there's nothing terribly weird about these elements. They're not made of different stuff. It's the ionization of the stuff that's weird. Nitrogen having lost 4 electrons. How do you do that? There's only 2 ways. The first electron, yes, of course, that was easy to do. Generally, how much energy does it take for the first electron to be lost, like from hydrogen? About 13.5 or a little more electron volts of energy will do it. How could that amount of energy get delivered to an innocent little carbon atom, which it could have a collision or radiation? Those are the 2 possibilities. Collisions, though, would have to be very high speed. You'd have to have very high kinetic energies. With 13 electron volts, how hot does the gas have to be? More than 100,000 degrees. This gas is not at 100,000 degrees. It's more like at 10,000. This might remind you of the spectrum of an H2 region where you also have ionized gas, except that gas is around O stars. Now, I'm showing you a different flavor of an H2 region around a quasar. They got some similarity and some serious differences here. But let's look at the similarity first. Why is there ionized gas in H2 region, for example, the O stars around the Orion Nebula? We need a source of photons that have a wavelength less than 9 or 12 angstroms or 91.2 nanometers. Sun doesn't do that. The sun has nothing down there. It's just pretty much a black body, and it's just not nearly hot enough. The sun is peaking in the visible. Now I'm asking for something at 15 times hotter than that. Do such stars exist? They're rare. In the Orion Nebula, they certainly do. It's the massive stars, right? There's 4 of them in Orion and the trapezium. Those O stars, which won't live very long, but while they're living, they're putting out a substantial amount of ionizing photons. The ionizing photons get absorbed by hydrogen, and they kick off an electron. They also kick off an electron from oxygen. They kick off an electron from carbon, from silicon, sulfur, and so on. No problem. We already knew about that. But what I want to call your attention to in this spectrum that makes the quasar, this is different from any O star. This is different from any H2 region. Each electron you knock off is more closely bound with more electric attraction to the nucleus. So it gets harder and harder, requiring more and more energy to knock the second one off. Knocking the third one off requires very high energy. And that's what's happened in some of these atoms that are around the quasar here. We're not talking about just ultraviolet, extreme ultraviolet energy. We're talking about practically low energy X-rays, so-called soft X-rays. The ionization potential to produce some of these ions here is not just 13 electron volts. It would be like 60 electron volts. And I can actually show you some emission lines in the spectrum. Oh my goodness. This one here is neon having lost 4 of its electrons. Requires like a few hundred electron volts. It's a signature of something crazy going on. The defining characteristic of quasars is that they put out a large total amount of their energy at very high frequencies. A lot of their luminosity is not just in the visible, it's not just in the blue, although they do produce a lot of that. It's in the extreme ultraviolet and the X-rays. That's really defining characteristic. There's none of that in Orion. There's basically none of that in O stars. It's something special about an AGN. And the theory says, oh yeah, that's because the inner parts of the accretion disk are much hotter than an O star. They're like 100,000 degrees. Even if it's like 2/3 of the way across the universe at a very high redshift. You can't miss these things. That most of these emission lines are quite wide. This hydrogen line is at least 100 angstroms wide. I've never seen anything like this in any normal galaxy. The rest wavelength here is, let's say, 5,000, but it's not all at that wavelength. Some of it's blue shifted, some of it's red shift, and the blue shifts and red shifts are like 100 angstroms out of 4,800, 1/50th, many thousands of kilometers a second, which of course would immediately escape the galaxy unless it was near something with an enormously high escape velocity. Very broad emission lines are only coming from a central point in the very center of the galaxy, right around the black hole central engine, nowhere else. Another clue. It's unstable. It's continually, unpredictably changing its brightness. So that means that all of this gas in the central region of this active galactic nucleus is being exposed to a randomly varying ionization source. That's certainly different from an O star. Just sits there doing its thing. So this accretion disk sometimes is sending out a lot of radiation, then maybe a few weeks later it's less radiation, then a few weeks later very little, then it comes back and it's really bright. It's brighter and fainter, brighter and fainter. What's the effect going to be on the gas? It's going to be responding by changing its ionization and changing its emission lines. These emission lines are just taking the UV photons that comes in and then just turning them into emission lines, reprocessing it. Comes in as Lyman limit photons. It goes out, for example, as hydrogen photons. The emission line region, this is called the broad line region, but this high density, highly ionized gas here should in principle respond to the amount of energy that's hitting it, and they change their brightness. They should change their brightness in response to a change of the central powerhouse, changing its brightness. But they're not right at the central powerhouse. They're some distance outside. They should respond to the changes of the accretion disk with a delay. The delay would be how long it takes light to travel from the black hole accretion disk. Suppose it gets more fuel. There's a new star available and it starts sucking it up and eating it up there. So it shines really brightly. So it's putting out a lot more UV photons. Well, then those photons have to travel out at the speed of light. That's what photons do until they hit the gas that makes these emission lines, the so-called broad line region gas. They only travel at the speed of light. And then you'll see the gas emission lines get brighter with a delay. It's called reverberation mapping. So you see the power source get brighter or get fainter. Either way works. And then the emission lines get brighter, get fainter, get brighter with a delay, which we could measure. We want to measure this delay time, the lag time of the emission lines. That tells us the size of this region. This has been done now dozens of times. I was the principal investigator of the first project that did this. I was kind of just a kid. We're sitting for 6 months using Hubble Space Telescope, which is pretty darn valuable, I can tell you. And like every day, it came back to the same Seyfert galaxy here, the same AGN. And fortunately, the AGN performed nicely, as they often do. The first part, it got brighter. Then it got much, much dimmer. Look at that, in a factor of 3 here. Then it got much brighter. And it got dimmer. And then towards the end of it, it got brighter and fainter again. Just what we wanted. Thank you very much, Seyfert Galaxy. Now, here are some of those broad emission lines. Don't they look similar? The broad emission line gets brighter. Then it gets much dimmer. Then it gets much, much brighter. Then not a lot happened. Finally, at the end, it gets much brighter, and then it gets dimmer here. I want to see if you can see this with your eye. Each of these ticks is 10 days. The continuum which is causing the changes changed first. And the continuum hits a peak about there. It hits a minimum about there. About 10 days later, the emission line shows its peak. And then about 10 days later, it goes down to minimum. Then about maybe 7 or 10 days later, it goes to a maximum here. So these emission lines are responding with a delay, which we said was about 7 to 14 days. You can see it in the graphs. This tells us how far out the gas is, the radius of the broad line region. I now know how far the gas is from the mass that's accelerating it. So I've measured R. The velocity measure, I just looked to see how wide the line is, right? So that turned out, in this case, to be about 3,000 kilometers a second. The mass of the black hole, which really determines everything about the system.